Hello and welcome to this recording learning on Xilinx Agile Mixed Signal HDL Design Flow. My name is Frank Nelson. I'll be your instructor for this module. This module introduces the HDL design flow for the Xilinx Agile Mixed Signal or AMS solution. This module targets FPGA designers who want to use the Xilinx AMS solution for their design. We will also look into some key features of the XADC core that helps digital designers implement an analog front end with the latest 7 Series and Zinc FPGAs. Now this module will cover some advanced concepts which designers can leverage for configuring the XADC core in their design. If you're new to Xilinx Agile Mixed Signal Solutions and want to learn more about it, then watch the What is the Xilinx AMS Solution recording on this same site. If you're an embedded designer and want to learn more about the EDK flow, then check out the Xilinx AMS EDK design flow recording as well. Now, after completing this module, you can go deeper with the AMS evaluation recording, which provides an in-depth understanding of how the AMS targeted design platform can be used to evaluate the analog interface. This module is also an introduction to our Designing with Xilinx AMS course. Now, we recommend that you take the time to attend this course and learn all the critical design considerations you must make when targeting any 7 Series or Zinc device using the AMS solution. This slide provides a brief overview of the design flow for designing a mixed signal design using a Xilinx FPGA. Now, the first step you would do is to design an analog-based system is to evaluate the XADC core for your platform for interfacing the sensor or the external signal you want to monitor. Now, the electrical output of the sensor or the external signal to be monitored must be conditioned to map to the input range of the XADC component. Then the XADC can be fine-tuned for performance by calibrating the analog sensor output. Calibrating the analog sensor output will remove the gain and offset errors induced by the sensor's transfer function. After calibration, the XADC settings can be documented and later applied while instantiating the XADC core into your design. The next step in the design flow is to instantiate the XADC core in your design. Now, you can configure the XADC core using the documented settings captured during the evaluation phase and then instantiate that into your design. Now, the XADC core can be configured either using the wizard or through block attributes written in HDL. Now, this module extensively covers the different ways of adding the core to your design in the design flow. Finally, you would perform verification of the FPGA design using the XADC core. The Xilinx toolchain supports verification of the design by providing a behavioral model of the XADC's functionality. We will also look at a simple example simulation later in this module to see how the simulation model for the core allows analog signals to be introduced into an HDL simulation flow. The XADC evaluation can be performed by using the 7 Series AMS Targeted Design Platform, or TDP. The XADC Targeted Reference Design, based on the AMS TDP, primarily targets analog designers to select the XADC settings and evaluate the XADC performance. After achieving the satisfying results, the designer can then lock down the XADC settings that meet the exact needs of the system. The settings can be documented and later be used while instantiating the core into the FPGA design. Designers can also leverage the ChipScope Tools debugging facility for evaluating the XADC interface as well. You should also consider watching the AMS evaluation REL to get an idea of how the XADC core can be evaluated using the AMS TDP. Now, the Xilinx XADC LogiCORE IP is present in the large list of 7 Series primitives. That's the library of macros that are included with our implementation tools. Now, the XADC LogiCORE IP is fully tested, documented, and supported by Xilinx. The XADC block is unlicensed and is provided free with Xilinx software. The customizable LogiCORE IP that applies to the XADC core can be seamlessly integrated into your HDL code, whether your design is built with Verilog or VHDL. This is an overview of the Xilinx primitives available in the Xilinx tools library. The XADC block has one dedicated external analog input pin pair, that's VP/VN, and 16 external auxiliary input pairs which use the dual-purpose IOs located on the FPGA. Now these FPGA digital IOs are individually nominated as analog inputs when the XADC is instantiated into the design. The XADC block has few control and clock nets. The ConVST net controls the sampling instant on the ADC input for the event-driven sampling mode. When triggered, the ConVST signal will enable the ADCs to sample the analog input and perform the analog to digital conversion. The XADC block also provides alarm outputs for internal sensor measurement if they are exceeded using the user-defined thresholds which you can customize. Other important signals are the status signals, which indicate the status of the ADC block and provide the channel ID being sampled. You can leverage these status signals to build any autonomous logic or state machines which can automate your XADC sampling and control process. After the analog signals have been accurately converted by the ADC, the converted digital information is available on the XADC status register set. There are 32 16-bit status and control registers which are available for users to monitor and control the XADC block. The XADC registers can be accessed from the FPGA fabric via the dynamic reconfiguration port. It is also possible to initialize these registers during the configuration of the FPGA. This enables the XADC core to start operating in a user-defined mode after configuration has been completed. Now there are 32 attributes associated with the XADC primitive that allow users to initialize these registers. These registers define the mode of sampling, channels to be sampled, sample rates, as well as other features. The two 12-bit ADCs can be configured and used independently in simultaneously sampling mode. The operational mode can be set by writing to the control registers of the XADC. The converted digital output of the two ADCs are available in two independent status registers. Now, if you want to understand more about the XADC block and its features, the Xilinx 7 Series XADC User Guide is the best place to learn more about it. Now, the XADC core can be integrated into your VHDL or Verilog code and is fully supported by the Plan Ahead and Project Navigator tool environments. The Xilinx tools provide instantiation templates that can be copied and pasted into your HDL code. The instantiation template for the XADC block is available under the Advanced Device Primitive Instantiation option in the language templates of both Plan Ahead and the Project Navigator. Now this is a Verilog example showing the instantiation of the XADC block. The example shows how the block's 16-bit registers are initialized by setting the attributes of the Verilog instantiation. This enables the XADC core to start operating in a user-defined mode after configuration has been completed. Below the initialization, we can also see how the XADC I/O is connected to the rest of your FPGA design. The designers who are comfortable manipulating the registers for the XADC settings can use this flow. Now, with the help of the 7 Series XADC User Guide, designers can configure the parameters of the XADC core. Some designers may want a much more interactive approach to configuring the XADC core. Such designers can use the XADC Wizard to configure the block. The XADC Wizard can be launched from the Core Generator tool within the Project Navigator or the IP catalog from the Plan Ahead software. The Core Generator software is a tool that manages information about each available core, organizes the cores for easier browsing, and creates the actual output files needed to integrate a core into your HDL design. Note that some cores require special licenses, but the XADC core does not. The Core Generator is installed automatically with the ISC software, and it's available both as a standalone utility and is integrated with the ISC Project Navigator, as well as the Plan Ahead environments. CoreGen is built to interface with many design entry tools in HDL design flows. Since most customers are using an HDL flow, we're going to focus on that flow. To launch the XADC Core Generator Wizard from the Project Navigator, you can use the command project new source to launch the new source wizard. We'll then select the IP, core generator, and architecture wizard option in the new source wizard. Then enter a file name for the XADC core that you want to use in your design and the path where you want to save the output from the wizard. You then click Next, and the core generator will then open with a GUI that allows you to select the type of component you wish to make. You can then expand the FPGA features and design, and under the XADC, select the XADC wizard options, and then click Next. From there, the XADC core generator wizard is launched, which provides a series of GUIs that allows you to customize the XADC core parameters as well as its other features. Now, to start CoreGen in the Plan-Ahead software, you simply click on Project Manager IP Catalog. Then you can expand the FPGA features and design, and under the XADC, you can select the XADC wizard option and then click Next. This will launch the same wizard that you would see from within the Project Navigator environment. The XADC wizard is an interactive graphical user interface, or GUI, that generates the core for instantiating the XADC block into your design. Using the wizard, the users can configure the XADC to operate in the desired mode. Now, the GUI allows you to select the channels, enable alarms, and set the alarm limits. You'll also note that the XADC wizard GUI changes with the mode of operation selected from the GUI. This prevents unwanted register combinations, which might otherwise be possible with attributes written in HDL. Now, it's a simple way to configure the XADC core for your design. The wizard will generate the HDL via a Verilog or VHDL flow for the required register settings and the I/O using an easy-to-understand GUI. Now, the core generator has a built-in user guide for the XADC core and describes the functionality and purpose of each customizable parameter from within the XADC wizard. The wizard user guide can be accessed by clicking on the Datasheet button present on the XADC wizard GUI. You can use this document to choose your options from within the wizard. Now, after selecting the configuration options, you can click Generate on the wizard screen to generate the HDL wrapper and other wizard outputs. The output files are placed in the project directory you selected when you set up the new core generator project. The XADC core generator wizard will produce an XCO file which describes the component's options and is used to create the core. Now, this file is automatically associated with the project hierarchy of the Project Navigator or from within the Plan-Ahead software. Now, the XCO core can be customized and regenerated by selecting the XADC core and choosing the appropriate process options in the toolflow area. Now, as mentioned earlier, the core generator supports HDL flows and is capable of generating instantiation templates. That's the VHO and the VEO files are the HDL instantiation templates for VHDL and Verilog respectively. Now, they are generated by the core generator based on the design entry options set from within the ISC software. You can select the XADC core in the hierarchy and click on the View HDL Instantiation template to view the Verilog or VHDL instantiation templates that are made by the tool. You can then copy and paste these templates into your HDL to include the XADC core into your design. Your HDL can be written to perform autonomous operations on the XADC for sensing the analog input. Now, again, check out the XADC user guide, that's UG480, before you code your state machines for the XADC. It provides detailed information about the XADC's operating modes and the timing information, which enables designers to code state machines to read and write to the XADC block. Now, the synthesis tool will infer the XADC hard block from the instantiated XADC component. This figure shows how the XADC block appears in Technology Viewer from within the Project Navigator. After adding the core to your design, it is best to perform a behavioral simulation to make sure the system is behaving as expected. This XADC HDL flow is tightly integrated with the Xilinx iSim simulation tool. The Xilinx core generator also generates the behavioral model file that you will require for testing your component with either ModelSim or Xilinx's own iSim simulator. The simulation model accepts input from an analog input text and not from a test bench. The analog test stimulus file is basically a simple text file that contains real or analog information and the corresponding timing associated with it. The analog stimulus text can be associated using the XADC model using the sim monitor file attribute while instantiating the XADC core into your design. Now this slide shows a Verilog example of how analog stimulus text file is passed as an attribute to the instantiated XADC model. Similarly, the analog stimulus text can be associated to the XADC model in the XADC wizard. The option to specify the file name is available as a field on page 1 of the XADC wizard. You can associate a valid analog stimulus file by specifying the name of the text file into this field. Analog information is introduced into the simulation along with the correct timing in this stimulus file. This analog simulation file is a text file that contains real values and the corresponding timing information. The syntax is straightforward and analog information from a range of sources can be used. For example, the output from a MATLAB model or actual analog measurement taken in the lab by the analog designer can be easily added to the verification of the digital design. The analog information must be formatted in a spreadsheet so that the first column contains timing information and the remaining columns contain the analog information, that's volts and degrees Celsius, for example. The columns can be in any order and only the required channels need to be listed. However, all columns must have the required label or header, i.e. the VCC internal, the temperature, the auxiliary input ports, the auxiliary end ports, etc. And this is required for proper identification in a simulation. Now you can code test bench drivers or monitors using HDL for the other modules which will execute in parallel with the XADC analog stimulus input. Now, in summary, the unique combination of a flexible analog interface via the XADC block and the programmable logic capacity of the 7 series FPGAs as well as the Xilinx 7000 offers an extensible processing platform, or EPP, and this offers a better way to scale and customize custom analog interfaces requirements at each and every design phase in your HDL flow. Now, the XADC settings are evaluated in the evaluation phase, where the XADC block is calibrated for the gain and the offset correction of your sensor input transfer functions. In the implementation phase, the XADC core is generated with the configuration settings evaluated during the evaluation phase and then instantiated into your FPGA design. Designers can leverage the core generator's XADC wizard, which is an interactive graphical user interface, or GUI, that generates the XADC block configured to your design's requirements. The designer can use the XADC wizard user guide to learn more about how to run their design through the XADC wizard GUI and explicitly configure the XADC options to operate within their desired mode. Now, the core generator's XADC wizard will generate the instantiation templates that can be used to instantiate the core into your design. You can then write your HDL to perform autonomous operations on the XADC for sensing the analog input. Refer to the XADC user guide, that's UG480, which is the detailed datasheet for this XADC block. It contains a detailed description of the XADC's functionality and a quick introduction with which the designer can learn the pinout requirements and determine how to instantiate basic functionality into the design. After adding the core to your design, you may want to perform a behavioral simulation to make sure it meets your system needs. While the XADC HDL flow is also tightly integrated within the Xilinx iSim simulator, the core generator also generates behavioral simulation model files that will require for testing your component with either model sim or use within the iSim simulator. Now, the simulation model accepts input from an analog input text and not from a test bench. The analog test stimulus file is basically a text file that contains real or analog information and the corresponding timing information. Well, there are lots of places to learn more about Xilinx FPGAs, and they all start at support.xilinx.com. To learn more about the Xilinx AMS system, visit the website you see here. This microsite is where you can find the latest and most updated technical information. You'll also find some additional white papers for Agile Mixed Systems solutions at this link. You'll also have the opportunity to learn more about AMS applications if you attend the AVNet AMS workshop at the 2012 XFest, that's the Xilinx Device Festival. If If you would like to register, check out the URL you see on this slide. However, if you have questions about the 7 series device family or features, you should check out the user guide or check out one of our free recorded e-learning modules, probably on the same page in which you got to this recording. If you would like to see what other courses we offer or what other free RELs are available, you can go to the Xilinx education link you see here. I'd also like to mention again that Xilinx offers a large number of instructor-led trainings worldwide, which cover topics from basic tool languages to detailed architecture training on the 7 series device families. But whatever you do, please take a second and let us know what you thought of this recording. Just click on the icon on the next page and tell us what you thought. Again, my name is Frank Nelson. You've been listening to the AMS HDL Design Flow REL. Thanks for your time and attention, and thanks for your business.